Hey, what's up? It's your old pal, Mr. Cook. We've got through the first 15 problems of the review. Let's see. I guess I'll do a couple more for this video, and then I'm going to call it a day, and I'll finish up the rest later. Okay, so 16 and 17, these look to be L'Hopital's rule problems, probably. Excuse me. So first thing I do when I see a limit, if it's got a value attached to it, like the limit as x goes to whatever, I always like plug the number in just to see if I don't need to do L'Hopital's rule, because it might just be something simple like, oh, it goes to 0, or it goes to infinity or negative infinity, so it doesn't exist, or it goes to a number, right? But if it's one of those special cases like 0 over 0, infinity over infinity, we've got to reevaluate it. Okay, so first plug in 0. Let's see what happens with this. So natural log of 1 plus 0 plus 0. So that'll be just 0. And then the bottom part, if I plug in 0, that's 0 to the third, which is 0. So 0 over 0 is L'Hopital. So that means that, I do the derivative of the top and the bottom. So the derivative of natural log of 1 over x is 1 over 1 minus x. And then times the derivative of the inside, which is a negative 1, plus the derivative of x, which is 1, plus the derivative of 1/2 x squared, which would just be x. And then that's all over derivative of x to the third is 3x squared. Okay, try to plug it in again, see what you get. Well, let's maybe make this look a little nicer. We get a negative 1 up top. And you know what? I'll probably just rewrite that as negative 1 and then 1 minus x to the negative first. That might be a little bit easier for me. So if I plug in 0, I get negative 1 over 1 plus 1 plus 0. So that's going to be 0 again. And then in the denominator, 3 times 0 to the second is also going to be 0. So that means that I get 0 over 0, which is going to be L'Hopital again. So I take the derivative. All right, so using chain rule for this, negative 1 out front gives me a positive 1, and then 1 minus x to the negative second, times the derivative of the inside, which is negative 1. Derivative of 1 is 0, derivative of x is 1, all over, and then that'd be 6x. So if I plug in 0, I get, let's see, that'd be negative 1 over 1 plus 1, so 0 again. And then the bottom, 6 times 0 is 0. So L'Hopital, and this will be the last time, because when I take the derivative of 6x, it's going to be 6. So it'll force it to either be a number or 0 overall. Let's see what happens. So limit as x goes to 0. Again, use the chain rule here. Let me put that negative out front also. There we go. Negative 2 times negative 1 would be a 2. So 2, 1 minus x now to the negative third, times the derivative of the inside, which is a negative 1, plus 0, because that plus 1 right there just becomes a 0, over derivative of 6x is just 6. So now if we plug in 0, we get 6 in the denominator, so I don't need to do the limit of the top, limit of the bottom anymore. And if I plug in 0 for the top, I get 2 times 1 over negative, the 1 to the negative third, so that's going to be 2, and then times negative 1 is negative 2, and then that'll reduce down to negative a third. So it looks like we do get a number at the very end, negative 1/3. All right, so there's our first one. Man, that was off with a fresh start. That was 3 L'Hopital's rules in one. Man. Okay, let's take a look at 17. So as we evaluated at infinity, let's see here. So here's what would happen with the algebra in the top part. So it'd be natural log of technically infinity. Now, don't ever write this on a test or on if you're doing a free response question or something, because they'll take points off, because that's not mathematically correct. You can't algebraically evaluate infinities. You can only use limits. So, but there are some things that you should remember just in your head for natural logs. Natural log of 0 basically goes to negative infinity. Natural log of 1 is 0. Natural log of e is 1. And then the natural log of infinity basically goes to infinity. Okay. So this part right here goes to infinity. And that means that you get natural log infinity in the top, which, goes to infinity. And then the bottom part obviously also goes to infinity. So infinity over infinity is a L'Hopital situation. So he's L'Hopital in this. So the limit as x goes to infinity of, and then natural log of x, that would be chain rule. So the derivative of natural log of something is 1 over that thing. So 1 over natural log of x. And then we need to multiply that by the derivative of the inside, which is 1 over x. And then the derivative of natural log of x is just 1 over x as well. Since we're not evaluating this at 0, we can just go ahead and see what happens as the 1 over x's cancel out. Another way to look at it would be this: if you're dividing by fractions, the same as multiplying the reciprocal, so that means that 1 over x is going to cancel out. Either way, this is the same thing as saying the limit as x goes to infinity of the 1 over x's cancel out, so 1 over natural log of x. And remember what I said, natural log of x, if we use the, if we use infinity for that goes to infinity. And so 1 over infinity, this whole thing, just goes to 0. So that means that 0 is going to be our limit. The limit as x goes to infinity of that original expression, natural log of x over the natural log of x equals 0. Okay, so there we go. That's 16 and 17. Let's see, 18 and 19. Yeah, let's see. All right, I'll see how I feel after this one. So there are 320 yards of fencing available to enclose a rectangular field. How should this fence be used so that the enclosed area is as large as possible? In other words, it's a maximum. This is optimization, because if you're trying to find the maximum or the minimum of some value given some rate or constraint, it's going to be an optimization problem. So it's a rectangular field, and we're supposed to fence it off using all the 320 yards. So if it's a rectangle, then these two sides will be x, these will be y. I'm going to take 2 of the x's and 2 of the y's. It should add up to all the fencing 320. We call this our constraint function. So we're trying to maximize the area. Area is equal to x times y. When we want to maximize something, here's our steps we take. We take the derivative. So we take the area function and take its derivative, set it equal to 0 to find the critical numbers, and then draw a number line to see where we get our maximum from. So that's what we're going to do. But to take the derivative of this thing, I got to get it in terms of, like, instead of x and y, just get it in terms of x. So that's where you're going to use this thing called the constraint function. We're going to solve in terms of one variable. Let's solve it in terms of just x. And then we're going to substitute it into this thing to simplify it a little bit. So I'm going to solve for y here. Y is equal to, let's see here, so that'd be 320 minus 2x, then divide by 2. If I divide everything by 2, I get 160 there and just regular x, so 160 minus x. Okay, so this is what I'm going to use to substitute in here instead of y. I'm going to write it like this: x times that stuff, 160 minus x. Now the derivative is really easy to find. If I just distribute in x, I get area is equal to 160x minus x squared. I want to find the derivative. A prime is going to be equal to 160 minus 2x. And then find the critical numbers. I said that equal to 0 because there aren't going to be any DNE situations because it's a polynomial. And then we'd add 2x to both sides. So 2x is going to be equal to 160. Divide by 2. X equals 80. So there's one critical number that I can find. Let's make sure that this yields a area maximum. So if I plug in 80 for my one interval, I go from negative infinity to 80 and 80 to positive infinity. And then I'd use the derivative function and use a couple test points to see what's going to happen. So maybe I'd pick like 0 and 100 or something like that. So if I plug in 0 to the derivative, I'd get 160, which is positive. So the graph's going to be going up, increasing. If I plug in 100, 160 minus 200 would be negative 40. So it's a negative. So it's going down like that. So it goes increasing and then decreasing. So that means that this has to be a maximum. And that gives me, the first part. So let's see. How should the fencing be used so that the enclosed area is as large as possible? So x is going to be 80. And then I don't remember what the units were for that. Yards of fencing. And then y is going to be, let's see here. So if I go back over to here and plug in my x value, 80 in there, 160 minus 80 is 80 again. So that means that the y value is going to be 80 yards as well. So this will maximize the area. There we go. A rectangular area of 10,000 meters squared must be enclosed by a fence. What should the dimensions of the rectangle be if you want to enclose this area in the minimum amount of fencing? So now this is just using the same problem that we had in number 18, but just the opposite because they give us the area. And remember the area is going to be x times y if we use the same diagram, which I think we can use in this case. So this is going to be our constraint function now. And then the perimeter function is going to be the one we're trying to minimize. So the perimeter for the fencing would be 2x's and 2y's. So if I wanted to solve for one of the variables, like maybe I'll solve for y in this case, it's 10,000 over x. And that's what I plug in over here for y. Excuse me. So that's going to be 10,000 over x. And now I'm going to do the same steps that I did in number 18. I'm going to take the derivative, set it equal to 0, find my critical numbers, and then, find where I get a minimum amount of fencing. So that's going to go decreasing and then increasing. Okay, so take the derivative. P prime is going to be equal to, let's see, that's 2 plus, and then 2 times 10,000 is 20,000. And if it's over x, that's just x to the negative first. So if I use power rule here, I'd get negative 20,000 x to the negative second. All right, so for my critical numbers, I plug in 0 for p, 2 minus 20,000 over x squared. That's how I'll rewrite it. So I'll move the 20,000 over x squared to the other side. And then cross multiply. So 2x squared is equal to 20,000. Divided by 2, x squared is going to be equal to 10,000. That means that x is going to be equal to 100, I believe. Well, plus or minus 100 for that. And then also, there is one more critical number here. So if p prime is equal to this, then that means that obviously x is not allowed to be equal to 0. So here's how I'd write up my number line now. So I'd have 100, I'd have negative 100, and then I'd also have 0 because 0 is not allowed in my derivative. So this gives me 1, 2, 3, 4 intervals, negative infinity to negative 100, negative 100 to 0, 0 to 100, and then 100 to infinity. And I got to show that like one of these is going to be a minimum, but I can exclude some stuff, right? Because I'm never going to have like negative fencing, so I can actually like get rid of these intervals altogether and just focus on these two instead. So I'm going to get 2 test points from in here. In between 0 and 50, in between 0 and 100, probably 50 would be the number that I'd use. And then something past 100, something easy, like maybe 200 or something. So I go back over to my derivative, and I see what happens in these cases. If I plug in 50, that would be 2 minus 20,000 over, let's see, 50 squared is 2500. So I think that would be, let's see, if I knock off 2 zeros there, 200 over 25, that's 8. So negative 6. So I get a negative number. And then if I plug in 200 to my derivative, I get 2 minus 20,000 over 200 squared. So that'd be 2 minus 20,000 over, and then 200 squared is 4, and then 4 zeros. So that's a half. And so that'd be positive, so it'd be increasing. So sure enough, this will be a minimum. So that means that 100 is going to be my local minimum value. So what should the dimensions be for this? Well, the x value should be 100 meters. And then for y, let's go back over to this equation because this will help me to solve for it because it relates x and y. If my x value is 100, and that means that I would get 10,000 over 100. So it just knocks off 2 of the zeros there. So 100 would be my other number. So that means that these are the dimensions that will get the smallest perimeter. And there's my answer for number 19. I think that's it. We'll just do these 4 problems, and that's it for this this video. Okay, well, I hope you found this video helpful. If not, go find your calc teacher, go talk to them. I'm Mr. Cook. If you need my help, just come by anytime in the morning or after school. I'll be there to help you out. Okay, on to the next video. See you later. Bye-bye.